Hi everyone, in this recording we're going to talk about manipulating graph data. We're going to be focusing on the tidygraph package, which gives an analog of the tidyverse, but for networks. We're not even going to be talking about any visualization. The reason is that usually before we get into any visualizations, there's some sort of data cleaning that has to be done, and data cleaning for graph data tends to be a little bit trickier than data cleaning for ordinary tabular data. So let's look at some of the tools that are available through tidygraph. Okay, so the first issue. The basic tension that makes data cleaning difficult in graph data is that all the information can be divided into two different kinds of data. There's information about the nodes, and then there's information about the links. And you can't really treat these the same way. So the way that tidygraph tries to reason about this distinction between nodes and edges is it creates a new kind of data structure which stores both the nodes and the edges as separate data frames but combined within the same data structure. And so here we have an example. High school is some data structure that comes in an example data set from the tidygraph package and is converted to something called a table graph. And you can see it's two different objects in one. So these are 70 students. The names are just numerical IDs. And then there are 506 edges. So these are edges between pairs of students. So these are edges from student 1 to student 13, 1 to 14. These edges actually have a time attribute, so the edges are changing from one year to the next. Okay, so that's kind of the basic tidygraph structure. It looks like a pair of data frames together. And what's really nice about this is it allows us to use something like the tidyverse mutate and join syntax, but applied to these sort of graph structures, right? So here I'm creating a new column on the nodes, and it's just randomly sampling two different colors. And you see I called mutate on that table graph object, and it's created a new column called favorite color here. It's left the edge data exactly the same, but now these nodes have some attribute. Right? So that's how you can mutate nodes. You can also mutate edges. So here I've generated random weights for each edge. So you can see here the edges. Right? The way I did that, I had to run this activate edges command. Right? If I didn't run activate edges here, the tidygraph package is going to be thinking that I'm trying to manipulate the nodes, and it would have created this weight column on the node data frame rather than the edges data frame. But with this syntax, I can now manipulate either of these data frames very easily. There's a really nice shorthand, so you don't even need to write this activate nodes or activate edges. You can use a special version of the pipe, right? So this %e arrow is going to be a pipe that goes directly to the edges, and there's a corresponding one with n, which goes directly to the node data. So from here, you can very easily manipulate either the nodes or the edges. Okay, so that's kind of the analog of mutate for tidygraph. There's also the analog of join. So if you've ever used ordinary dplyr, you know you can join two data frames together using left join or full join. Right? You can here join together two graphs, right? So if some node appears in several graphs and you have different edges specific to each graph, you can join them together into one unified graph by using the graph join function. So here I've just generated two random graphs. One of them is like a ring graph. The other one is some bipartite, like kind of pairs graph. And I've joined them together into one super graph. And you can see here, this is what it looks like. So this was the first one, here's the second one. And now this is combining the two graphs together. Right, so right here, A was connected with B and J. You see B and J, but it's also connected to F here, F and E. So, and the F and E edges came from this bipartite graph. Okay, so that's a kind of another kind of verb that you can use that came from the ordinary tidyverse, but it's now applied to the graphs. And there are lots of analogs, right? So you're familiar with filter from the tidyverse. You can also apply filter to tidy graphs, right? So here is generate random weights, filter those that are less than 0.2, and then sort the edge data frame according to the weight. Okay, a little bit more complicated and a little bit outside of what you would usually do with just ordinary tidyverse. You can also start doing certain kinds of graph algorithms, right? There are a bunch in the tidygraph documentation. Some example, you can use something called group Louvain, and this is going to do a clustering, right? So behind the scenes, it's looking at the original graph, and it's trying to say, if this subset of nodes is tightly interconnected, but not too highly connected with some outside nodes, I'm going to assign them to the same cluster. And this function will actually pick the number of cluster nodes, right? So here, I just ran mutate. Since by default it works on nodes, it's going to change my node data frame. And now I have some cluster assignment for every single node. And here's just, you can see the plot. The nodes that are more tightly connected with one another have been assigned to the same cluster. We're going to go over the details about how you actually draw the edge and nodes using the gggraph package. But for now, I just want to make the point that you can take that original graph object and then apply all these manipulations to it. Okay, so those are some of the built-in kinds of graph algorithms. You can actually define your own graph algorithms using different kinds of mapping functions, right? So sometimes you need to do a lot of calculation node-wise or edge-wise. Trying to do this manually could be really tedious, but then the tidygraph package gives some functions that allow you to do this looping over nodes or looping over edges and do a small calculation within each. So an example here, this is looking at the size of the neighborhood for every single node. So what I specifically mean is it's going node by node, looking at all the other nodes within 2 steps away. So that's what local size order equals 2. It looks 2 steps away and it computes the size of that subset of nodes, right? And then it's added that to my node data frame, right? So it's calculated some derivative statistic that if you were trying to do this manually, it would have been pretty tedious. But then you can kind of do this automatic loop and topological query within tidygraph. Okay, so from here, you have quite a bit of flexibility in both cleaning your data. So you might imagine you start with certain columns and you want to filter, you want to redefine a new column by mutating it. You now have tools for doing that in graphs. You also have tools for if you want to derive any new statistics, right? Maybe you want a cluster assignment. Maybe you want to get something like the neighborhood size. All these sort of graph algorithms, they are a lot of helpers in this package that can make it so when you eventually do get to visualization, you have the kind of summary statistics and kind of clean data that you need.